Hi everyone, this is lecture 2 on neuronal function. Here we're going to review the principles of electrophysiology which you learned in SCB 203 for skeletal muscle and heart, and we're going to now then apply them to the nervous system. Neurons are similar, but in a way they're a little different. So our objectives for today are going to talk about leak and gated channels, which you learned about in SCB 203. We'll review the resting membrane potential, how it's formed, and what happens to it when in excitable cells. Here we'll talk a little more about local potentials and action potentials, okay, which you talked a little bit about at the neuromuscular junction in SCB 203. And then we're gonna describe how action potentials are generated and propagated. So let's start with the beginning. Ion channels are proteins that are required for all ions to pass through the plasma membrane. As you recall, ions are charged and they cannot pass through the lipid bilayer. So they require these protein channels that form little holes in the membrane so that they can flow through. There are two main classes of ion channels: leak channels and gated channels. Now, leak channels, as you might expect, they're always open, and ions will move down the concentration gradient into or out of the cell, depending on the ion. So here in this diagram, I've circled the leak channel, and you can see that it's always open. Okay. Gated channels, as you might expect by its name, has a little gate or a door that closes at rest and opens in response to certain stimuli. So it has a little gate that will open and close. And there are three types of gated channels: ligand gated channels, voltage gated channels, and mechanically gated channels. Ligand gated channels open in response to a chemical that binds to a receptor site on the channel. Okay. In SCB 203, you learned about the acetylcholine receptor. That was an example of a ligand-gated channel in which two acetylcholine molecules bind to the protein to open the channel up. Here, in this second one, we circled the ligand-gated channel. You can see in the left picture it's circled, meaning it's closed, and on the right one, the ligand is bound, and now it's open. We also have voltage-gated channels, which open and close in response to changes in voltage across the membrane. Okay, and these you learned about in SCB 203 because they're present in skeletal muscle, cardiac muscle, and you might have talked about it in smooth muscle. Okay, so in voltage-gated channels, a voltage change will either open or close the channel with little gates that respond to the change in voltage. Finally, we have mechanically gated channels, which open and close in response to a stimulation such as stretch, pressure, or vibration that physically manipulates the environment around the channel. So here, this last one are mechanically gated channels. So here you can see a probe pressing down that's going to stimulate the channel to open. Okay, so this is sort of like a pressure sensitive channel. So these are the basic types of channels in a cell. Now let's talk about the ionic gradients of a cell to refresh our memory from SCB 203. Now, most cells, the extracellular sodium is higher than inside the cell. So more sodium outside the cell than inside the cell. Okay. However, cytoplasmic potassium is higher inside the cell than outside the cell. Now, my notation here, if you took chemistry, is that whenever you have a bracket like this surrounding an ion, you read this as concentration. So this would be most cells, the extracellular sodium concentration is higher than in the cytosol. Now, if there's more sodium outside the cell and more potassium inside the cell, sodium will always constantly leak in through the channels into the cell. Potassium would always leak out from inside to outside the cell. However, there are maintained high amounts of sodium outside the cell and potassium inside the cell due to the sodium-potassium pump that's always working to put back the sodium and put back the potassium. Okay. Now, let's talk about the resting membrane potential. And you talked about this in SCB 203. But we'll make sure everyone's on the same starting point before we go too much further. Okay. So the resting membrane potential. A potential forms when you have separation of charges across a membrane. Okay. Now, this potential is called a voltage, and it's a type of electrical gradient. Because one side of the membrane has one voltage, and the other side is the other voltage. Okay. The electrical gradient across the cell membrane is the membrane potential, notice abbreviated as the VM. So VM is the membrane potential. Now, you learned that the inner membrane is negative relative to the outside of the membrane at the resting membrane potential. So the voltage of the inner membrane is negative relative to the outside of the membrane. Okay. And this occurs at the resting membrane potential. Since it's negative on the inside and positive on the outside, we say the cell in this state is polarized. Okay, and you can put a voltmeter to a person, to an organ, or to the cell, and you can measure the membrane potential. Okay, it's going to be negative on the inside and positive on the outside. So here on a neuron, they're measuring the axon, and they see that the membrane potential is at minus 70 millivolts, meaning it's minus 70 inside relative to the outside. Now let's look at the formation of the resting membrane potential. Now, the ion concentrations favor diffusion of potassium out of the cell and sodium into the cell, down to concentration gradients. However, they don't equally leak. Potassium is a little more leakier than sodium, so more leaks out than does sodium. Okay? And when it does this, this allows the outside of the membrane to be slightly more positive than the inside. So that's one reason why it's negative on the inside and positive on the outside. Okay. The other reasons is that the sodium-potassium pump is electrogenic, meaning it's putting 3 sodiums out of the cell and 2 potassium in the cell. 3 positive charges are more positive than 2 positive charges. That makes the inside, again, negative on the inside. There's one other reason why it's negative on the inside is that there are many negative charged proteins close to the membrane that also makes it negative on the inside. So there are multiple reasons why the inner membrane is negative relative to the outside. Now let's talk about the electrochemical gradients. Okay. So there's electrical gradient and a chemical gradient, and together they form the electrical chemical gradient. Okay. So in other words, diffusion of ions can be determined by 2 factors: the concentration gradient, which is the chemical gradient, or the electrical gradient, which is the electrical part of the gradient. The combined forces is called the electrochemical gradient. Okay, so let's take a look at this for potassium. Remember, potassium is higher inside the cell, so its concentration gradient favors the movement of potassium to the extracellular fluid, okay, from inside to outside. Okay. However, the electrical gradient favors the movement of potassium to the cytosol. Why? Because remember, it's positive on the outside here and negative on the inside, and potassium is a positive charged ion, so it's more happier inside the negative charge inner membrane, and it gets repelled by the positive charge on the outer side of the membrane. Okay, so here the concentration gradient, or the chemical gradient, favors it to move out, but the electrical gradient favors it to move in. So which one wins? Well, the concentration gradient is slightly stronger, so there's a small force that favors potassium out into the extracellular fluid. So for each ion, there are 2 factors: the electrical gradient as well as the chemical or concentration gradient. Okay. Now, if we use sodium, sodium will have both a chemical gradient because it's favoring into the cell by its concentration, but it's also favored electrically because it's negative on the inside of the membrane, so opposites attract. And so for sodium, both the electrical and the chemical gradient are favored. move into the cell. Okay. Now we know you discussed in SCB 203 action potential, so we know that the resting membrane potential in excitable cells can change. And we have specialized terms for these changes, such as depolarization, repolarization, and we're going to introduce a new one called hyperpolarization. Okay. Depolarization is the opening of gated sodium channels and allows sodium down their electrochemical gradient and rush into the cell. So the mass movement of sodium into the cell causes depolarization, and the resting membrane potential, which is negative to begin with, now becomes positive. As a result, the cell gains positive charge, making the resting membrane potential positive. And we can measure this as a slight depolarization as it becomes more positive. Okay. So here it's gone to minus 60 millivolts. Okay. So even if it's a small amount, it's still a depolarization. Anything that goes positive from the resting is considered a depolarization. What about repolarization? When a cell returns back to its resting membrane potential as sodium channels close, and now it's going to return back to the resting membrane potential. Okay. So here's repolarization and depolarization, and as it goes back, it forms repolarization. Okay, for some reason they don't show a figure showing repolarization. What about hyperpolarization? Now, this may occur if voltage-gated potassium or anion channels open, and the membrane potential may become more negative than the resting membrane potential. Okay, this is hyperpolarization. So here we see the resting membrane potential, and it becomes more negative. That's considered a hyperpolarization. So it's hyperpolarized, more negative. Okay. But now we have another type of potential when we're talking about nervous tissue, and this is called local potential. Okay, and you actually talked about a local potential indirectly when you were talking about the acetylcholine receptor, because remember that binding of acetylcholine to the acetylcholine receptor causes sodium and potassium to leave the cell, so it allows sodium and potassium to enter the cell. So that will slightly depolarize the membrane. That's considered local potential because it has to have enough sodium to enter the cell for it to open the voltage-gated sodium channels. Okay. Local potentials are also called gradient potentials because they can be different sizes. They can be small or a little bit larger. Okay. So it's a small local change in the membrane potential of a dendrite or cell body. However, they can be depolarizing or hyperpolarizing. So for the acetylcholine receptor, that was depolarizing. But in nervous tissue, we can also have local gradient potentials that are hyperpolarizing, that are more negative. Now we have several characteristics of local gradient potentials. Well, one of them is that it's graded, meaning that they can be smaller or larger. The secondly is that they're reversible, meaning if it's not big enough, it'll just revert back to the resting membrane potential. Okay. And finally, it's decremental. What does this mean? Well, that means farther away from the source, it gets smaller and smaller. Okay. Whereas, if you remember action potentials, they were all the same, all or none, and they're non-decremental. Okay, so that's exactly what we're going to talk about next. Action potentials. So action potentials are uniform, rapid, and all or none depolarization and repolarization of the membrane potential. If you remember from this, the action potential for a skeletal muscle, it just went straight up to positive, and then as potassium channels opened up, it repolarized. Okay. In the nervous system, though, action potentials are generated by what's called the trigger zone and send along the axons to another neuron, muscle fiber, or gland. Okay, so let's look at the events of an action potential. Neuronal action potentials have three general phases. Depolarization, okay, that's nothing too different. We have repolarization, again, that's not too different. But what's unique about neuronal action potentials is that they often have, it's called a hyperpolarization. There's an overshoot as potassium leaves the cell and makes it a little more negative than the resting potential. Okay, and of course, each of these phases are result from the opening and closing of ion channels. Okay, so let's look at the development of an action potential. Okay, so suppose a local potential reaches threshold. See this threshold right here? That's the threshold for a voltage-gated sodium channel to open. So if a local channel reaches threshold, the voltage-gated sodium channel will open up and it will begin to depolarize. Okay, and as more sodium enters, it depolarizes to a positive value. Okay. Now, as sodium channels close and now potassium channels open, now potassium is starting to leave, it's going to begin repolarizing the membrane. Now it's going to come back down towards the resting rim potential. Okay. Now sodium channels are closed, more potassium is leaving, and it's going to repolarize the membrane even further. However, what's different from skeletal muscle and cardiac muscle is that there's often an overshoot of the potassium that goes below the resting rim potential before it adjusts back, and that's hyperpolarization. Now, just like we had in cardiac muscle, nervous tissue also has a refractory period. And remember, our refractory period is when the cell is limited to how often they can fire an action potential. Okay? So the refractory period is the time the membrane cannot be stimulated to fire another action potential. And there are two parts to the refractory period. There's an absolute refractory period and a relative refractory period. Okay? Now, the absolute refractory period does not allow additional stimulation no matter how strong it can produce an additional action potential. So no matter how strong it's stimulated, it will not produce another action potential during that absolute refractory period. Okay, so right here, in this area right here, these two blue panels here is the absolute refractory period. You cannot produce another action potential during this time. Why? Well, because the sodium channels are opening and then closing. Now, before they can be activated again, they have to inactivate. And then they have to recover from an activation before they can open again. And they recover from an activation after the absolute refractory period. Now, we enter the relative refractory period, where a stronger than normal stimulus can produce an action potential. So here we have the relative refractory period. Okay, the sodium channels are in a resting state, but a larger than normal stimulus can produce another action potential here during the relative refractory period. So let's look at a comparison between now local and action potentials. Here on the left side are the local potentials, and on the right side are action potentials. So remember, we use these descriptions for local potentials. They're graded. They can be different sizes. They're reversible. They can return back to normal. And they're decremental, meaning they get smaller as you go further away from the source. On the other hand, action potentials are not graded. They're all uniform. One action potential is the same as another. They're irreversible. Once you start an action potential, like lighting a fuse, you cannot stop it. It's all or none. And it's non-decremental, meaning that it does not get smaller as you get further away from the source. That's it. You can still propagate. Oh, that's our next topic, the propagation of action potentials. Okay, so action potentials must be propagated along the axon. Because remember, we said the axon was its function was to propagate the action potential. The movement creates a flow of charged particles or current. So action potentials are self-propagating. Propagation occurs in one direction, and propagation forms the nerve impulse. Okay, and here the propagation of action potentials is kind of similar to that in skeletal muscle, where depolarization of the membrane causes the opening of voltage-gated sodium channels that allows sodium to enter. This will depolarize the membrane next to it, to open more voltage-gated sodium channels, and during the process, the action potential seems to propagate along the axon. So first it's here, and then it moves to the next area. Okay. Now it doesn't go backwards because remember the channels are recovering behind it, so it can only go one direction. So here, the sodium channels are then activated as depolarization occurs, and now moves down further down the axon, while behind it is being recovering. Okay, and finally, still it opens up further voltage-gated sodium channels as it propagates along the axon. Now, what we're showing also here is that potassiums are opening at their threshold as the sodium channels are closing, and this is going to help repolarize the membrane behind the propagation of the action potential. Now, not all neurons propagate action potentials at the same time, or at the same rate. They have different rates of propagation. Now, the conduction speed is determined by two factors. One is the diameter of the axon, and the other is the presence or absence of the myelin sheath. Larger axons have lower resistance to conduction. Okay. Same thing with larger blood vessels. So it's a physical property of cables. Okay. So larger axons have lower resistance to conduction, and they will conduct faster and more easily. The other factor is that there's the presence or absence of the myelin sheath. Okay, remember, some axons may be myelinated, others are not. Now, in the presence of the myelin sheath, a process called saltatory conduction can occur, which allows the propagation of the action potentials to go faster. And early on, it felt like it was jumping along the axon. That's where the saltatory comes in. But we know it's not really jumping, but it just appears like it is because it's going so fast. So the flow of current is more efficient in a myelinated axon and slightly faster. Okay. So here's this saltatory conduction of myelinated axon, and the reason why is that the myelin sheath insulates the loss of ions where it's surrounded, and then at the areas of the nodes around VA, it can be depolarized further and then move along the axon. So it appeared that the potential was jumping from one node to the next, but in reality, the action potential is propagating within the axon. Okay, but in the absence of the myelin sheath, of course, you can still have action potentials, but the conduction is continuous and occurs in the absence of the myelin sheath. Okay, so here it's just slower, but it's continuing along the axon. Now, there are different types of axons classified by their conduction speed. There are three main classes: A, B, and C. So here I made you a table of type A fibers, type B fibers, type C fibers. And notice that there are different sizes. Type A is the largest, type B is the intermediate size, type C is the smallest. Now, type A fibers are nearly all myelinated, type B fibers are mostly myelinated, and type C fibers are not myelinated at all. And you can now predict their conduction speeds. Type A fibers being the largest, and nearly all myelinated, has the highest conduction speed. Type C fibers, which are smallest and are not myelinated at all, have the slowest conduction speed. Type B fibers are sort of intermediate between the two of them. Okay, and here we show you examples of where you might find these types of axons. So type A fibers are found in sensory axons from joints and muscles. That needs to be quick. And motor axons to skeletal muscles. Type B fibers are efferent fibers from the autonomic nervous system. and sensory axons from organs. Okay, and the slowest ones are other efferent fibers of the autonomic nervous system that are not so critical, and some sensory axons that transmit pain, temperature, certain pressure sensations are also a function with type C fibers. Okay. So the conduction speed of the different axons are based on their size and whether they're myelinated or not. Okay, so here's a summary slide of everything we talked about. Okay, so remember we have local potentials that are found in the dendrites, and then we have the trigger zone where if it's significant enough, action potentials will be produced, which will then be propagated along the axon as if it was jumping from one node to the next. Okay. And here this figure is showing the propagation of the action potential as it depolarizes by opening voltage-gated sodium channels and repolarizing behind it by voltage-gated potassium channels. And due to the myelin sheath, it's insulating it so that there's no loss of conduction, velocity, or ions as they're insulated. And at each node, there are voltage-gated sodium channels will maintain the depolarization to the next node. Okay, so this is sort of a review from SCB 203, and there are very strong similarities to the nervous system, but there are also some differences. So we're going to go a little bit further in the next lecture now.